So this week we're talking about simple harmonic motion, and in particular, you can see my cat climbing up the back of my chair. We're going to be talking about springs and the motion associated with those. There are two common types of simple harmonic motion, one that has to do with springs, the other that has to do with pendulums. I'm sure you're talking about this in your actual class, at least pendulums. We are not going to focus on pendulums today because they're not part of this lab, but we will talk about spring motion. But the big common factor about this kind of motion is, so for a spring, we have a spring and then some object. And if we displace this object a certain amount of space away and then let it go, we know that it's going to go back and then forth. And this motion right here can be characterized by a sine or a cosine graph, right? Where this is the furthest away it's going to be, this is the closest it's going to be, and then this is the equilibrium position. Some terminology that you might see, this right here is called the amplitude of the wave of the thing. So this is the maximum distance that it achieves away from its equilibrium position. And then a full wave is measured from like a peak to a peak right here. We'll just do this in another color so it's easier to see. From a peak to a peak right here. That is called a wavelength. You can measure from other parts too. You can measure from a trough right here to the next trough over here, or from an equilibrium point to its corresponding equilibrium point over here. We're not going to do a whole lot with this, but it's good to know. So specifically, when we're talking about springs, there is a force associated with a spring. And that is Hooke's law. If you haven't seen this already, this is a really, really good one to know. So the force that the spring is exerting on an object is equal to negative some constant coefficient times the displacement. This constant right here is usually called the spring coefficient. And it's measured in units of newtons per meter. The delta X right here is how far from equilibrium. Equilibrium, or I guess like natural spring length, this is just how long the spring is when it's not being pushed or pulled. And then this negative sign is very, very, very confusing. So my recommendation to you when you're working these problems, when you're doing the math, ignore the negative sign. And then at the very end, look back at your free body diagram, figure out what direction the force of the spring should be pointing, and then either put a negative sign or a positive sign. So I guess, for instance, if I have a spring that's like this, and right here is its equilibrium point, but I've stretched it, and so I have my object way out here, I can tell that the force on this box right here, the spring force is pulling it to the left. And if I am assigning a positive and a negative sign to my system, then I would say that the spring force is less than 0, or it's negative, it's in the negative direction. Whereas if I'm holding on to this so that it's not moving, then there's some applied force that's greater than 0, that is positive. Conversely, if I have pushed the spring right here, I have applied some applied force in this direction. I can say, okay, that's to the left, so this will be less than 0. The spring is pushing back, so it's pushing in this direction, so the spring force should be greater than 0. It should be positive. And that can be seen due to the delta x right here. This is a positive delta x, and then this right here is a negative delta x. Again, negative signs are going to trip you up a lot in this. Just know why there's a negative sign there. It is because it is opposing the direction of the change in x. Scale from 1 to 5, how much does that make sense? And feel free to tell me 1 if it makes absolutely no sense at all. Okay. So of the 3 people who have spoken, very middling. Okay. I'm going to do a practice problem in a second. Actually, why don't I do that problem now, and then I'll come back to the calculating the period. So, John, you're asking if we put the negative sign after the math. Yeah, it's not rigorous, but here, why don't I show you this problem, and we can figure out it together. So in this system, I have a spring with a spring constant of 20 newtons per meter. My equilibrium point is right here, and my delta x from the equilibrium point is positive 20 centimeters, right? Because if I'm saying that to the right is positive and then to the left is negative, we've got that. So what I need to do right now is I need to figure out what is the spring force. How much force is the spring applying to this object? Note that we're not looking at the spring by itself, but rather the force that the spring is putting onto this object. So I would use Hooke's law. I'm going to take the negative sign out just for a second. K delta x. I'll plug in K, which is 20 newtons per meter, and then be very, very careful, right? Because this is 20 centimeters. This is newtons per meter. So I need to convert 20 centimeters to meter, which is 0.2 meters. And if I do this math, I should get 4.0 newtons. Now what I can do is I can look at the picture and I can be like, okay, is the force of the spring pulling backwards or pushing forwards? And I guess just use common sense, right? Like if you take a spring and you pull it, what direction is that spring pulling on you? And I look and I think I can pretty much say with certainty that it's pointing towards the left, which means I need to put a negative sign here. So that is the force of the spring on this object. Now, imagine the problem here was asking you, whoever you are, have taken your hand and pulled this weight backwards, and you're holding it in place. When you see a problem like that, the first thing you should do is draw a free body diagram. So I have my object. I have my applied force in this direction. And then I have my opposing spring force in the opposite direction. And then, I guess technically I have a normal force pushing up and I have a gravitational force pulling down. If the problem says you're holding it at rest, we can say that Fs plus Fa should be equal to 0, which means that Fa should be equal to negative Fs. So if I plug in what I got here, we should find that the applied force should be 4.0 newtons. That is the force required to hold it in place that far away from the equilibrium point. Okay, so if it was pushing, it'd be minus k times negative d, and Fs would be positive. Yes, in fact, why don't we do that practice right here? Same setup as before. The spring is the same. The equilibrium point is the same. But this time I have pushed 40 centimeters away from the equilibrium point. So I would put in Hooke's law. I would say K is 20 newtons per meter. And then I would say the displacement here, I'm just going to do absolute values for now. I have done it 0.4 meters from equilibrium. Remember, this is not an SI unit. In order to get the meters to cancel out, I need to convert to meters. So then I look at this and I say, I have to do math now. What is this? 8? Yeah, 8.0 newtons. And then I can think, okay, what direction is the spring force pushing? And that's a clear thing. It's pushing, right? So, well, obviously, it's pointed in this direction. So I can put a positive in front of it. Yeah. Is this making a little bit more sense now? Like scale from 1 to 5, is it making sense? Sick. Yeah, let's go. Okay. Yeah, remember that in physics, negative signs are most of the time just telling you direction. They are still important, and you should know why they're there, but you can usually figure out why they're there based on the physical concepts. Yeah, cool. Now, I'm gonna clear my notes here because a common problem that you will see, and one that will be on this lab, is you'll have a vertical spring. You'll have a spring that's hanging from the ceiling. And usually it's going to have some equilibrium, or sorry, it will always have an equilibrium point, or that's actually, okay, let me back up. Equilibrium point is not the correct term. Natural length is the correct term. This is the natural length of the spring. But let's say I take a weight right here with some mass M, and I hang it on here. It will stretch the spring beyond its natural length. And then it will come to what is called the equilibrium point. And the equilibrium point is when the sum of all of the forces equal 0. This is, I think I've told you this before, this is the Greek letter sigma. This represents you sum up all of the forces. When you see a problem like this, again, the first thing you should do is draw a free body diagram. So I have my box. It is being pulled down by the force of gravity. I know this because we are on Earth. Then, if it's an equilibrium, there has to be an equal magnitude force upwards. That is the spring force. So in this situation, our negative sign will depend very much on, do we define up as positive or do we define down as positive? I'm going to define down as negative. So obviously the force of gravity is equal to mg. which means that the spring force, I guess, if I'm saying that this is negative, if the force of gravity is negative mg, then the spring force must equal positive mg to counteract the downward force. And we can learn a lot of really cool things from this setup right here, because we know what the equation for the spring force is. I'll do it in a different color over here. The spring force, the Hooke's law, Fs is equal to negative k delta x, with or without the k, who knows. So if I know that, I can put k delta x is equal to mg. So let's say I know what the delta x is. I measure this, and I say that this is 30 centimeters. But I don't know what k is. Well, if I know what the mass is, let's say the mass is 10 kilograms, and let's say g is equal to 10 meters per second squared, I can see that k times 0.3 is equal to 100 newtons, and then I can just solve for k. And I can find out what the spring constant is for this spring. And that's actually what a lot of this lab is going to be doing. But before we move on to the lab itself, I want to go back really quickly and talk about another important part. And that is the period of the spring. So if you just imagine in your mind's eye, you have a spring hanging, there's a weight attached to it, you pull that weight down and you let go of it, it's going to start bouncing up and down. And in the real world, that will eventually slow and come to a stop, because there's things like air resistance and friction and a whole bunch of other things. But in an ideal non-frictional vacuum, hypothetically, this spring, this mass on a spring, is going to bounce up and down forever. And this equation right here tells us how long it takes to go from its highest position down to its lowest position and then back up. So AKA one wavelength. And you'll notice right here that it has nothing to do with gravity. The period of a spring on Earth is the same period of a spring on the planet Mars, on the planet Jupiter. It doesn't matter. And you'll also note it has nothing to do with how far from equilibrium it is. So if you pull it 100 meters down, its period of oscillation will be the same as if you pull it like 5 meters down. This is a property that only exists for springs. Pendulums also have a period, but that one does indeed depend on gravity. So don't get confused in your actual class and thinking that it doesn't, because this does not have anything to do with springs, or sorry, with pendulums. Yeah. Are there any questions about this or anything about springs so far? Sweet. In that case, let me show you the lab really quickly. When you follow the link, you'll come to like this right here, and then you can follow it. We're not going to use any of the first three. Oops. We are just using the fourth one, the lab. This is the setup. It's going to have a lot more information than we actually need, but it also has a lot of good information. So here's our spring. You can change the spring constant, but don't. Keep it on this third position right here. You have a mass that you know the weight of, sorry, you know the mass of, and you can change that if you'd like, but for most of this, you're going to leave it at 100. And this is 100 grams. Remember that for a lot of our stuff, we have to use kilograms. So this is actually 0.1 kilogram. When you're doing the lab, don't forget to change that. You can take it and you can hook it. You can see that it's going to bounce up and down. You can hit stop to get it to its equilibrium position. You can actually change the gravity of where you are. You can be on Earth, the Moon, Jupiter, Planet X, and you're actually going to like derive the accelerations due to gravity on each of these celestial bodies based on the spring. This is one of my favorite labs just because you get to do like interesting things like this. But yeah, you can turn damping on or off. I think there's no part for this lab that you need to keep it on, so you can just turn it off and keep it off. Some other very helpful pieces are this right here. It shows you the natural length of the spring. Remember, that is the spring when it's not stretched. And then the green is the delta X. The green is how far it has traveled. You can see the mass equilibrium. This is where it is at rest. And then you have like a movable line that you can move yourself if you want to. When you're setting up the experiment and you do this, it's going to bounce up and down, and it's going to do this forever. If you want to measure, you know, the equilibrium position, just hit the stop button and it will do that for you. Let's see, there's one other thing. There's mystery masses that you're going to have to derive the masses of. And then for one part of the experiment for the lab, it's going to require you to time something. And it's kind of impossible. Oh, sorry, there's a ruler here that's very, very useful. Note that it is in centimeters and not meters. You're going to be asked to like pull something down and then like time how long it goes through 20 oscillations. And it's kind of impossible to like release it and then quickly hit the start button and keep it accurate. So here's what I recommend you do. This is an advantage that we don't have in real life. You can pause time. If you hit the pause button right here, time has been paused. I can pull this as far down as I want. I can hit the start button on the stopwatch, and nothing will happen until I start time again, and then it will start it all at the same time. And I can count for like, what, 20, and then once it goes through 20 oscillations, I can hit stop, and that can be my recorded time. Remember that an oscillation or a period is a full coming back to where it was before. So if you start down here and you let go of it and it bounces up here and then it comes back down, when it comes back down, that counts as 1. And then when it goes up and then down again, that's 2. And that's the lab. It's pretty easy. It's one of my favorites. The simulation's very simple to use. Questions? Excellent.